Welcome back to some more Solidity smart contract vulnerabilities. In this one, we're looking at denial of service, right? The DOS vulnerability. And even if you don't know anything about smart contracts, you're most likely familiar with this type of vulnerability, right? Anything to deny service, the service that you expect is, unable to do its job, deny service, that's the vulnerability. But how does it actually look in Solidity? That's what we're going to look at here, right? So the vulnerability is exactly what you think, but, how does it look? So one example is, if you loop through externally manipulated mappings or arrays, you could actually have a DDoS if you let the user supply an array that the code has to, the contract has to loop through, right? Because if an attacker sends a ridiculously long array or mapping and the contract has to go through and perform some function on every entry in the array or mapping, then it is going to, bring it down, or it's at least going to take really long, and it could actually bring it down because one nuance to these smart contracts is that you will have a maximum gas that is allowed, and that is set, I believe, when you create the contract, and actually deploy it to the blockchain, you set like a maximum amount of gas that the contract is allowed to take up. And that basically prevents the contract from using like ridiculous amounts of gas, right? But what can happen then is, say that you have some kind of limit on that is low enough that an attacker passes in an array that is larger than that it will take more gas to perform the function that many times than you have set for your limit. Then what's going to happen is that function is not going to be able to operate. It's going to be completely inoperable, which effectively will deny service. Bring your contract down. So that's basically what's going on in this code snippet here. Sorry if that explanation was a little bit convoluted. Basically here they're allowing the user to supply an array. And we'll see in a minute the remedy for that. Basically, don't let the user supply the array or the mapping, right? Supply it yourself so you know what the length's going to be, or at least provide some kind of checks against the length of the array, the number of entries in it, so that it won't bring down the service. The other way is owner operations. So, for example, if an owner has specific privilege, like they manually have to call finalize on a contract to allow the tokens to be transferable, the issue is that if that one address, the owner of it loses the private keys, or if it becomes inactive for whatever reason, then basically the entire contract becomes inoperable. So basically, if that's your scenario, as is here, then all the Ethereum or whatever the token is going to be locked up in the contract, because that address, the only address that is capable of calling finalize to divvy the tokens out, can't call finalize because they don't have access to that address anymore. So yeah, don't do that. Definitely don't be the one denying service to your own contract. And then number 3 is progressing state-based on external calls. I know it sounds a little bit complex, but all that's going on is, basically it says contracts are sometimes written such that in order to progress to a new state requires sending ether to an address or waiting for some input from an external source. So these patterns can lead to DOS attacks, like in the event that the external call fails or is prevented for external reasons. So you want to make sure you're checking for those conditions in your code before you deploy anything into the production Ethereum network, obviously. Because, just one call that fails could bring your whole contract down in that case. So preventative techniques here, right? So a withdrawal pattern for the first case is recommended for that example of that arbitrarily large array or mapping. If you can provide it so that you're not accepting arbitrarily long stuff, then you can ensure that you're not going to get anything that is more gas than you have your limit set to, and you'll be able to process whatever comes in. And then in the second example, required to change the state of the contract. In such examples, wherever possible, a fail-safe can be used in the event the owner becomes incapacitated, right? So, I mean, obviously, yeah, that one is a pretty simple case. Like, you're relying on one address that someone could lose their private key to, could lose access to. Have a fail-safe, right? If you're going to have to go that route, at least have a fail-safe. So, potential solution could be setting up the owner as a multi-sig contract, or you could have a time lock where the require could include time-based mechanism. So you could have something like this that'll unlock at a certain point automatically. So depending on what you specify in the unlock time, just in case something goes wrong, right? And yeah, they're talking about centralized alternatives. That's interesting. I didn't even catch that on the first go around, but yeah. So where you could use a centralized solution where one can add a maintenance user who can come along and fix the problems with DOS-based attack vectors if need be. Typically, these kind of contracts contain trust issues, though, over the power of an entity. Yeah. So, yeah, in that case, you're kind of defeating the purpose of decentralization, but if it doesn't really matter to you, I suppose you could do that. But yeah, when you add that in, you are introducing some potential vulnerabilities, potential issues now with your contract. So just keep that in mind if you want to go that route. In real world example, apparently there was some Ponzi scheme, some old Ponzi scheme called governmental that accumulated quite a large amount of Ether. In fact, had 1,100 Ether, which back then wasn't nearly as much as it is today. But it was unfortunately susceptible to DOS vulnerabilities. So basically, all that Ether, all that 1,100 Ether was locked in the contract because the mapping, the deletion of the mapping had a gas cost that exceeded the block gas limit. That's the first case that we mentioned in this video that happened to this contract here. And yeah, all that Ether was basically locked forever in there. No one could get it out. So yeah, the ramifications are pretty costly for this type of vulnerability. So if you're developing anything on the blockchain, make sure that you do not fall victim to these vulnerabilities. Hopefully this helped you. Or if you're a security guy on my side, you understand some potential vulnerabilities and how to exploit them. Of course, in a non-black hat way, hopefully. But yeah, good to know this stuff for sure. I'm definitely enjoying this. Let me know if you are as well in the comment section down below. And if you want to get caught up on the series, maybe there's some more videos you want to watch, or if you just want to rewatch some, I have them on the screen right now. The smart contract vulnerabilities are in this playlist. So go ahead and I'll see you guys over in those videos. Thanks for watching.